Hi Year 12, so now we're on to the actual questions from paper 2. So SL Kayvon, your question numbers will be slightly different probably throughout the paper, so just keep an eye on that because there will be a different number of questions for HL students. So I've noted at the top of each question which SL question it corresponds to. So in 3A, a raindrop falls vertically from rest. State the initial acceleration of the raindrop. Okay, so here's your raindrop. We know that initially it has its weight, mg, acting down. If it is starting from rest, it is not falling with any velocity initially, that's 0 meters per second. So we know that it's not falling through any air initially, so there is no air resistance. So the resultant force is mg, and F equals ma for the resultant force. So therefore, the acceleration is g, is 9.81. So you should have just said 9.81 to start with. Lots of you said 0, which I assume is because you read it as from rest, but that's the velocity is 0, not the acceleration. Okay. So in 3b, it tells you that the graph shows how the speed of the raindrop varies with time t. So you can see the speed increasing but at a decreasing rate until it reaches a terminal velocity. The gradient of this graph is acceleration. We can see that initially the acceleration is positive but decreasing to 0. So, explain by reference to the vertical forces how the raindrop reaches a constant speed. So, firstly, we need to actually think about what the vertical forces are. So you need to have referred to the weight of the raindrop and then the air resistance of the raindrop. Those are the two forces. So weight acts downwards, which is constant the entire time. But first mark point, as velocity increases, the air resistance increases. So to be clear, you get 1 mark for having identified air resistance, and you get 1 mark for saying that as the velocity increases, so does the air resistance. And then the third mark comes from saying so that the resultant force on the drop decreases to 0. Okay, at the point where the weight and the air resistance cancel out. So my 3 coloured bits are the 3 marks. So 1 for identifying the air resistance, 1 for identifying that the air resistance increases as velocity increases until the resultant force is 0, because the weight and the air resistance have cancelled each other out. So in 4a, a ball of mass 0.25 kilograms is released from rest, u is 0, at time t is 0, at a height h above a horizontal floor. The graph shows the variation with time t of the velocity of the ball. Air resistance is negligible. Take g to be minus 9.8 meters per second squared. The ball reaches the floor after 1 second. So we can see in the graph that the start of the bounce is at 1 second, and the bounce, so there'll be some compression of the ball, will take this long. The bounce ends at this point. Okay, so what we see is that we have a ball starting at a height h and it is falling down. Velocity is down. We take that to be negative, okay? The velocity values are all negative and increasing because the ball is accelerating, okay? So negative velocity just means downwards, and the value of the velocity increases because it's getting faster as it falls. It's accelerating due to gravity, okay? So the gradient of this graph is 9.81 because air resistance is negligible, okay? At this point here, it hits the floor, okay? And it quickly has its velocity reverse direction. It goes from being negative to positive, which means that the ball's direction is changing from down to up. And hopefully you can also see that there must have been some energy lost because it leaves the floor with 5 meters per second, whereas it started hitting the floor at 10 meters per second. Okay, so there was energy loss during that compression. Okay, so this is the bounce. At this point here, the ball is still at the floor. Okay, but the ball now is moving away from the floor in the upwards direction. Okay, so the velocity is all positive, i.e. moving upwards, but decreasing in value because it is decelerating because weight acts against it. Okay, so this section where velocity is decreasing, the ball is moving up, but it is slowing down because of gravity. Okay, when velocity is 0, sometime later, this is the ball at its maximum rebound height. Okay, so think about it carefully. The bounce happens at 1 second. It goes from moving down to moving up. Velocity becomes positive. At this point here, the ball is on the floor and is moving away from the floor and is slowing down because of deceleration due to gravity until it reaches a velocity of 0. That is its new highest position. Okay, so it's rebounced up to its highest point. And again, now, if you look, velocity switches to be negative. The ball is falling back down and increasing in velocity because it is accelerating again. Okay, so that's just an explanation of how the graph is working. So the next page says determine H. So we're going to go backwards. Okay, H is the initial height above the horizontal floor. Okay, so we know that the ball was dropped from rest. Okay, so this is time t equals 0. We know that the ball is traveling downwards to the floor at this point. The bounce happens at this time. Okay, so this must be its position as it reaches the floor. So that is its final velocity. Okay, but what we can do is say, okay, well, let's look at the Suvat equations we know. S is equal to uv plus a half at squared. Well, we know that u is 0, so that removes this term. We know that we can take acceleration to be 9.8, although I've just immediately done 9.81 just because it's just what I know. You'd actually be fine either way. You get the same number to the same number of significant figures. So S is a half at squared when u is 0. The acceleration in this case is g, so I can take this section, okay, because I know how long it took to reach the floor. It took 1 second, okay, and so all I'm doing is a half times the acceleration during that time multiplied by that time squared to get 4.9 meters, because it's at this point that I have reached the floor, and this is from H at this point. So we should have got 4.9 meters. In 4b, it says label the time and velocity graph using the letter M where the ball reaches the maximum rebound height. So again, let's look at this. We did discuss this when I went through what the graph shows. The ball is falling, hits the floor, so velocity becomes positive, so it's now moving upwards. Okay, so in this section, the velocity is all positive. Okay, it's still moving upwards, but it's slowing to a stop at its highest position when v is 0. So this is its maximum rebound time, okay? That is when it will be at its maximum height above the ground again. So that's at 1.6 seconds. In 4c, draw on the axes a graph to show the variation with time of the height of the ball from the instant it rebounds from the floor until the instant it reaches the maximum rebound height. No numbers are required. Okay. Well, we saw from the previous graph that the velocity decreases to 0 from a maximum value during rebound to maximum height. Okay, so let's look at it again. We know that we are looking from the instant it rebounds until the instant it reaches a maximum rebound height. So, rebound happens, maximum height. Okay, so we can see the velocity is decreasing to 0 during this time. Okay. We know that velocity is the gradient of this graph. So as we know that the velocity decreases to 0, at which point it's at its new maximum height, we know that the gradient of the graph has to decrease to 0. Okay, so it should be that we're increasing in height, but the rate at which we're doing that is going to decrease because we're going against gravity. Okay, and when we're at a maximum height, velocity is 0. So the gradient at the end should be 0. So that's what your graph should look like there. Okay, 5a then. A string of length 0.8 meters is fixed at both ends. The diagram shows a standing wave formed on the string. P and Q are two particles on the string. Okay, so let's just consider the scenario. Okay, we've got this piece of string. It's oscillating, so I want you to imagine point P is kind of going round and round and round, and then point Q is also going round and round and round, but the circle that it moves in is smaller in radius than for P. Okay, so P and Q do not move physically left to right. They are just moving in a circle at their fixed position on the x-axis. Q's amplitude is clearly smaller than P. Okay, the radius of the circle that Q moves round is smaller than the radius of P. And also, at any given point in time, they are out of phase. Okay, P is at maximum positive amplitude, while Q is at maximum negative amplitude. So they are out of phase. So then it says the variation with T of particle P is shown. Could you draw on the axis a graph to show the variation of T for Q? So 1 mark came for drawing them in antiphase, okay, because when P was positive, Q was negative. And now instead of it being a graph against position, we're saying at an instant in time, where is P, where is Q for its displacement. Okay, so at exactly the same time, P and Q need to be out of phase, so Q needs to start down at the bottom. And then in the second mark point comes from recognizing that the amplitude just needs to be smaller. It doesn't matter how much smaller, it just needs to be smaller than 2. Okay, so 1 for each of those. In 5b, it asks you to calculate the speed of the waves on the string. So if I just zoom out a little bit so we can see where I got the first bit from. We are told that this entire length is 0.8 meters from here to here. Okay, we can see that we have 1.5 wavelengths fitting in there, so 3/2 lambda. So that 0.8 meters in length corresponds to 3/2 lambda. I rearrange that and I get 1 mark for the wavelength. Okay, and then I just use my wave speed equation, V equals F lambda. I don't have the frequency, but I do have the time, and I know that frequency is 1/time. Okay, so if I replace this F with 1/t, I get lambda/t. The other thing that people didn't spot is that the values were in milliseconds. And when you plug that in, you will get 190 meters per second. For 5C, this was done pretty well. A couple of you had a few little mistakes, so just be careful and make sure you've made your corrections. Outline 2 differences between a standing wave and a travelling wave. Well, these were your options. Don't give 3, give 2, but I've just given you more so you have options to remember. Travelling waves transfer energy, standing waves don't. The amplitude of oscillation is fixed with position on a standing wave. This is one that some people had muddled up, so one to be really careful of. It's variable on a travelling wave. So if we go back to the previous diagram, a position is just a position along the x-axis, okay? At any point, the amplitude at that point is dependent on where it is along this line, okay? The amplitude of P is fixed. It will always be this value, okay? The amplitude of Q will always be this value, okay? So from the equilibrium point to here or the equilibrium point to here. A travelling wave, the peak moves along, so P at this position on the string will sometimes be up here, but then later will be found in different positions. So the amplitude of oscillation is fixed for a particular position on a standing wave, but is variable on a travelling wave. Or you could have said standing waves have nodes and antinodes, whereas travelling waves don't. Okay, in 6A then, 2 loudspeakers, A and B, are driven in phase and with the same amplitude at a frequency of 850 Hertz. P is located 22.5 meters from A and 24.3 meters from B. The speed of sound is 340 meters per second. Okay, first things first, we can work out the wavelength for 1 mark. Lambda is V/F. We are told V and F in the question. So you got 1 mark for identifying that the wavelength is 0.4 meters. 1 mark came from saying what the path difference was, which comes from working out how many waves fit between AP and BP. So we know the total length of AP. We divide it into number of wavelengths, so divide it by 0.4, and we can see that we can fit 56 1/4 wavelengths. between AP. And then you do the same for B, and you work out you can get 60 3/4 wavelengths. So the path difference for a wave travelling from A compared to B, reaching point P, is 4.5 wavelengths. That's the difference between these two. Okay, so writing either 1.8 meters or 4.5 wavelengths gets you a mark there. Waves from A and B therefore meet out of phase, 3rd mark. Therefore, destructive interference occurs, 4th mark. Okay, 6b. When both loudspeakers are operating, the intensity of sound recorded at Q is I0. Loudspeaker B is now disconnected. Loudspeaker A continues to emit sound with unchanged amplitude and frequency. The intensity of sound recorded at Q changes to IA. Estimate the ratio of IA to I0. Okay, so if we disconnect loudspeaker B, the total amplitude available halves. Okay, because we've lost half of the amplitude. Because remember, the total is just the sum of A and B normally because of superposition. So we've halved our amplitude. You then need to recognise that the intensity is proportional to the amplitude squared. So if the amplitude halves, then the amplitude squared is going to change by a factor of a half squared, which is a factor of a quarter. Okay, so we now have a quarter compared to the original. If I0 is 1, IA will be a quarter. So the ratio is just a quarter. In question 7, a power supply is connected to 3 resistors P, Q and R of fixed value and to an ideal voltmeter. A variable resistor S formed from a solid cylinder of conducting putty. This is important. Okay, there's a set amount of putty, that's going to be important later, is also connected in the circuit. It's moulded so that the resistance of S can be changed by reshaping it. The values of P, Q and R are 40, 16 and 60 ohms respectively. The EMF is 6 volts, internal resistance is negligible. Good, yeah, so I have actually redrawn this circuit so we don't have to keep flipping backwards and forwards. So, the first thing is it asked you to calculate the potential difference across P. Okay, so this is my redraw. So we had P here. We just needed to know the voltage drop across there. So we were told, I should say, we've got 6 volts across the cell. Let me just do a double check on that one. Yeah, so we know 6 volts is being shared. So, if we track round, an electron will either go up to P or down to Q. So it will go through P and then R. So, coming back up, the branch that has P on it contains P and R that are 40 and 60, the total resistance being 100 ohms. Therefore, the P resistor, which is 40 ohms, is going to take a 40 out of the 100 total share of the voltage. Okay, so it's going to take 4/10 of the 6 volts, which is 2.4 volts. That bit was pretty straightforward. You really should be getting that bit. The next bit is a little trickier. The voltmeter reads 0. Determine the resistance of S. So I'm going to zoom out. Hopefully we'll still be able to see everything clearly enough. We need to have a look at what happens here. Okay, so we know if we are an electron at this point, and we're just thinking about conventional current for now. Obviously, we know electrons genuinely move from the negative plate, but just consider for a second. At this point, the potential is 6 volts for every coulomb of charge because it hasn't had to go through any components yet, so it still has the full 6 volts, 6 joules per coulomb to transfer. At this point here, the potential is still 6 volts. Nothing has happened. We know that the potential difference, the voltage across P, was 2.4 volts based on having just calculated it in the previous question. So if I started with 6 but I transferred 2.4 away, at this position here I have the difference. I have 3.6 volts. Okay, and then I spend 3.6 or transfer it more accurately in language. I transfer 3.6 volts across R before I come back and gain another 6 volts. So we know the PD across S is going to be 3.6 volts. We know the PD across Q is going to be 2.4 volts. Okay. We Okay, to be clear, the reason we know the PD across S as being 3.6 is because of the fact that it tells us that the voltmeter reads 0. That's really crucial because it means that what we're saying is if we compare the potential at this point to the potential at this point, they are the same. The potential difference is 0. Because we have recognised that we dropped 2.4 volts across here and therefore we're at a potential value of 3.6, it tells us that because we see a 0 difference between this point and this point in the circuit, this one must also be 3.6. That's what tells us 3.6 volts is the drop across S. Okay, so that's how we get this point. We know that 6 volts in total has to be transferred across QS, so we know that these two values have to add up to 6, so that's what gives us the value of the PD across Q. Okay, so from there I can work out the current, because I now know that the current through this entire branch is the same everywhere. That's a series part of the circuit, so the current through Q equals the current through S. I can work out the current through Q because I have the voltage and the resistance now. Okay, so the 2.4 volts that's dropped over Q divided by the 16 ohms gives me the current, which is 0.15 amps, travelling into S. Okay, I know that RS, resistance of S, is the ratio of the voltage to the current. We know that we have to drop 3.6 volts across S now to be at our 0 point before we go back to the battery. And we know that the current is the 0.15, and that gets us 24 ohms. In 7C, a couple of you got this right. This was a tricky one, so well done. Okay, all the putty is reshaped, okay, but all the putty still exists. So the key thing that you should have understood from that is that the total volume of the cylinder is unchanged. If it is 4 times longer, it must be that the area is a quarter, okay, because we know that the volume of a cylinder is the cross-sectional area multiplied by the length. If L is times 4, A is times a quarter for the total V to remain unchanged. So we now have two factors that have changed. The length has changed and the area has changed. We know that resistance is proportional to length, and we also know that it's inversely proportional to area. So therefore, we've got a factor of 4 increase for the resistance because of the length, but 1 over a quarter for the factor of the area. So the resistance total changes by 16. I take my previous resistance, which was 24, I multiply it by 16 and I get my 384 ohms. In 8A, the graph shows how the current I varies with potential difference V across the component. Lots of you had the right idea, but you didn't really respond to the question properly. It says outline why component X is considered non-ohmic. So you need to refer to the graph really. The current is not directly proportional to the voltage. It is a non-linear graph for component X. For the mark there. In 8B, component X and a cell of negligible internal resistance are placed in a circuit. A variable resistor R is connected in series with component X. The ammeter reads 20 milliamps. So first things first, I have a graph for what the voltage is across X for different current values. So I'm going to go back, I'm going to go to 20 milliamps. I'm going to track across, and that corresponds to 2.3 volts. There was a little tolerance there that you were allowed. Okay, so I know that when I is 20 milliamps, the voltage across X is 2.3 volts. I can therefore work out the voltage across R, which means that I can then work out the resistance. 4 minus 2.3 is 1.7, so the voltage across R is 1.7 volts. Resistance is voltage divided by current, so I take that voltage divided by the current because it's a series circuit, and I get 85 ohms. In 8C, power dissipated, P is IV, total current multiplied by total voltage. Everyone, I think, got that one right. Maybe some of you got the unit of power wrong, so just be careful there. It's watts, not joules. In 8D, we've got component X and the cell are now placed in a potential divider circuit. So you've got the original circuit drawn here. It's going to go on to say, state the range of current that the ammeter can measure as the slider is moved from Q to P. So I've drawn it out so that you can see what this actually really looks like when it's at Q and when it's at P. So if the slider S is touching at the bottom of Q, essentially what you have is PQ and then a junction where you can either go straight back to the cell. So if you imagine charges coming through PQ, if the slider's down here, you can either take the path this way or you can take the path through X. But because it's just a wire with no resistance, it causes a short circuit. So X is not included in the circuit at this point, so charges are not going to do that. They're just going to go straight back to the cell, so no current will flow through X at that point. So the minimum value is 0. If the slider is at P before P starts, essentially what you have is a parallel junction of possibility to go through PQ back to the cell or through X, which means that the voltage across PQ is the same as X. X will take 4 volts because that's what's supplied from the cell. And if we go back to the graph and we look at 4 volts, we track up, that corresponds, sorry if that's a bit hard to see, 4 volts corresponds to 60 milliamps. So that's my maximum value here. And so my range that I'm going to write there is 0 to 60 milliamps. In 8E it says, describe by reference to your answer for CI the advantage of the potential divider arrangement over the arrangement in B. So we're saying, why is this a better option where we have a slider compared to just 2 resistors in series where one is variable? Okay, well in this case, we always have to have charges flowing through both, so we can never have no current in X. Okay, and it also means that there has to be a voltage share at all times between these two, whereas down here we can either completely short X out, making the current 0, or at maximum we can actually give full voltage from the cell to X. So we have 2 things to write. It allows 0 current to flow through X, 1 mark, and it provides a greater range of current that can flow through X, 2nd mark.